Hey. So today will be a bit more chatty. I'm going to talk about dynamics and gravitational waves. This is the observational consequences of the phase diagrams and bubble nucleation that we've chatted about in the last few days. So I'm going to start just by drawing something I've drawn before, which is temperature versus our order parameter. And in this abelian Higgs model, we had a case where at high temperatures we were in a symmetric phase where our order parameter was nearly zero. And then at low temperatures, there was some critical temperature, let's say here, where it jumps to some new value. And this plus the fluctuations is what we would expect our order parameter to do if it followed equilibrium. But because the universe happens in a finite amount of time, it can't always equilibrate, and jumping from here to there is a very slow process governed by this bubble nucleation or vacuum decay. And so the cosmological trajectory typically follows something like staying in the symmetric phase for longer, and then later on joining the other equilibrium. So this is our Cosmo case. This is our equilibrium case. So we'll look a little bit more about the dynamics of that today. We already kind of looked a little bit about where does this start. So you can see here, I'm assuming we're staying in the symmetric phase a little bit longer, and then it kind of starts to tick up at some moment. So where does this happen exactly? And we looked last time at this quantity I called gamma, which is the bubble nucleation rate per unit volume, or the vacuum decay rate per unit volume. And when this is about Hubble to the 4, is when we get the kind of beginning of this uptick. And we'll call that time just T0. So it's the kind of if I were to give a name to this time, it would be the one bubble per Hubble time. Where on average, if I draw a Hubble patch, I've just nucleated one little bubble in it. And that's kind of the beginning. But if we want to know how this evolves, we then need to think, okay, how does this bubble evolve? So inside the bubble we have the new phase, and outside the bubble we have the old phase. And as this happened after some supercooling, the new phase is energetically favored. The new phase is really the equilibrium phase if we had time to reach it, which means that the pressure inside is higher than the pressure outside, because the pressure is minus the free energy, and this has a lower free energy. So, as a consequence, this thing is going to grow. The volume of the bubble at some time t, given that it nucleated at some earlier time t dashed, so this is the, let's say, nucleation time. And this is some later time. So the volume of the bubble is going to be equal to 4 pi on 3 times the radius cubed, where the radius is something like the initial radius plus how much it's grown. And here we've assumed that it's going to grow at a constant speed. Of course, at the beginning, it's not going to grow at a constant speed. It'll accelerate, something will happen. But at very late times, or if we look at times where this volume is much bigger than the initial bubble, so that we can drop this as negligible. So we're considering times where the bubble has grown lots. then for most of the time, the bubble should have been at a roughly constant speed. Either it reaches some kind of a steady state solution, or even if it doesn't reach a steady state solution but keeps accelerating, it's going to get near c. It's going to get near the speed of light fairly quickly, and then it'll basically stick at 1. Or if it doesn't get to the speed of light, it'll stick at whatever its steady state solution is. So there'll be some kind of a constant velocity for most of the evolution of this bubble. And so that's its volume. That's the volume of one bubble. Really what we want to know is how much of the universe is in one phase and how much is in the other phase. So let's first define what the thing we want to understand. And this is I'm calling it h of t, h for the high temperature phase, as in the symmetric phase. And this is the fraction of the universe in the high T phase. And in the context of our abelian-Higgs model, this is the one that's normally called the symmetric phase. So this would be the quantity we kind of want to calculate. This is equivalent to the probability if I take a random point that it's in the high T phase. So there's equivalent definitions. Now, if we start, it's easiest to calculate this if we start at a time where there aren't that many bubbles. So near T0, when there aren't too many bubbles, we expect that the fraction of the universe in the high T phase is 1 minus something, where that 1 minus something is, let me just write it and then we'll chat about it. Let's put an approximate equal there. So this is 1 minus. So I have an integral over all times since let's say this is the critical time, equivalent to the critical temperature, when bubbles could first start forming, integrating up until the time I'm interested in. And over that whole time period, I'm going to integrate the nucleation rate at those different times by, so this is an earlier time t dashed, so I'm nucleating at t dashed, and then I'm growing the bubble from t dashed, when it was nucleated, to a later time t. So this is nucleate at earlier time, grow to later time, and then integrate over all the possible times I could have nucleated. Hopefully that makes some sense. The problem with this is it doesn't account for possible overlaps of bubbles. So this is our kind of a leading order approximation, which makes sense at this kind of a time. But if we want to think about overlaps of bubbles, imagine simulating the universe twice, where this is the probability of producing bubbles per unit time, and then they grow like this. So if you simulate two boxes, and you get some bubbles produced, and then you want to kind of combine the statistics there, you could combine the bubbles which don't overlap into your new picture, but whenever there's a bubble that's overlapping, you don't want to double count those regions, because in the regions inside the bubble you can't nucleate, you can only nucleate outside the bubble. So you need to get rid of the double counting of overlapping bubbles when you're doing that. But you don't want to get rid of both bubbles that overlap, you only want to get rid of half of them, because otherwise you're undercounting. So the next term will be a plus a half times this thing squared. And if we keep going, the combinatorics is going to give us an exponential. So actually, what we find is the exponential of minus the integral from Tc to T of this same quantity. And this is the fraction of the universe in the high temperature phase. Okay, so we looked a little bit at how to calculate this as a function of, well, I guess as a function of temperature when you know the potential. And this is going to be, we know this is an exponentially strongly varying function because the general form of this was like some functional determinant times e to the minus action. And the action bit is going to change with time or temperature. So this is going to be some exponentially strongly varying function of time, whereas this is just polynomially. So when I'm doing this integral, my rate is increasing, and this integral is going to be completely dominated by the upper limit, or somewhere near the upper limit where this rate is largest. Because towards Tc, the nucleation rate is 0, and then it grows and grows, and then towards the end, you're going to produce the most bubbles. So, so as gamma T primed exponentially growing, most bubbles are produced near T dashed equal to T. And near that point, we can approximate gamma of T dashed by A e to the beta T. That's because we're only going to need this upper limit, and near the upper limit, it's going to have some non-zero slope, and this is just the slope of the exponent near that upper limit. In which case, we can then do this integral. And because it's going to be dominated by the upper limit, I can extend the bottom of I can extend the lower integration range to minus infinity. And then we have A e to the beta T times 4 pi on 3 VW cubed T minus T dashed cubed. And this is now an elementary integral that I can do, and it is indeed dominated by this upper part of the integral. And I get A times, sorry, this should have been T dash there, because I'm integrating over it. We get A times e to the beta T, and I'm going to get, I have to integrate by parts 3 times, and I'm going to get a 6 on the top here, which gives me 8 pi VW cubed all over beta to the 4. Yeah. Sorry, it's meant to be to the 3. It's just my handwriting. Was it the same question or no? No, this is just because the potential is varying as a function of temperature. And so if we have your 2 minima as a function of temperature, one minima goes down, and consequently the barrier, which was also higher in the middle, the barrier also goes down. So it's just easier to nucleate at lower temperatures. And because the universe is expanding, later times is lower temperatures. That's the physical picture. Oops. And I guess we could put that in, and we find that h of t is the exponential of minus some constant, which is 8 pi VW cubed A over beta to the 4 times e to the beta t. And this is just a constant, that bit here. Yeah. Yeah, but it's a gamma function of 4, which is 6.
Why do we integrate them from minus infinity to t instead of from 0 to t?
So this integral, it was initially, I had this Tc time, and near this Tc time, this is not a good approximation to my rate. So in some sense, this lower limit, I don't really know the answer or what it looks like there, but I do know the answer that it should be 0, it should contribute very little. But because of this approximation, the lower limit doesn't contribute. So I can put it wherever I want and I'll get the same answer.
But even gamma is 0 being like beyond the critical temperature. Like there is no, like it's not possible to transition if you're above the critical temperature. So I think it makes sense to integrate from minus infinity, which would be like temperatures above the 0, right? Does it make sense?
So say that again.
I'm saying that gamma, the transition rate, is 0,
Is 0
above the critical temperature.
Indeed, yeah.
Or at times before the critical time.
Yeah.
Right?
But by moving this a little bit, I'm going to make an exponentially small correction to this. So yeah, it's going to be plus another term where it's e to the beta and then a different time which is exponentially smaller. So it shouldn't matter. But going on to this form now for h of t. So I've just put in this result and I've commented that this is a constant times e to the beta t. So I can essentially repackage this constant and we get the exponential of minus e to the beta t minus tf. And this is a definition of tf. So I've just put this as a time where this exponential, the exponential inside the exponent has exponent 0. So I'll just leave this for a moment. What is this tf time? So h of tf now is e to the minus 1, which is 0.37. So that's somewhere there. So I've now found a time somewhere in the middle where an order 1 fraction of the universe is in the high temperature phase and an order 1 fraction of the universe is in the other phase. So, yeah. In fact, this TF is a little bit more special than that. And if you want, show that the rate of change of H is maximal at TF. I mean, it's not difficult to show that, but this TF time is the time in which this is changing the most rapidly. The universe is changing the most rapidly. So in terms of bubble collisions, it's the time where the most area of bubble is hitting the most area of other bubbles. So the volume is changing the most rapidly. And from this, we can calculate other things, essentially by integration. So if you want to know the number density of bubbles, so how far apart they are, how dense they're distributed, we'll then integrate from Tc up to T of the nucleation rate times the probability that I'm in the high temperature phase, because I can only nucleate within the high temperature phase. So this product gives us how readily at a given time bubbles are nucleated, and then if I integrate that from the initial time to some later time, I'll get the number density of bubbles. And from that we can define an average distance between bubbles as the number density of bubbles to the minus 1/3. And this is the average distance between centers. And as we kind of saw, in the end, the crucial quantity is this beta. Beta is what determines the time scale of the transition. TF is just a special time where stuff is really happening, and then beta determines everything beyond that. So the average distance between bubbles is then going to be dominated by beta, determined by beta, and it's equal to 8 pi to the 1/3 times VW divided by beta. And again, see if you can work that out if you fancy. Now, everywhere I've had t, and t is slightly awkward given all of our computations before were not in terms of time, but in terms of temperature. So we want to switch out time for temperature to get a better handle on what's going on and to relate it back to what we were doing before. So we're thinking of radiation-dominated universe after the hot Big Bang when it's cooling down, and during radiation domination, we have that the scale factor times the temperature is about constant. And crucially for us, if we want to take a temperature derivative, then this is equal to a minus the logarithmic. Sorry, the time derivative is equal to minus the temperature derivative, like this. So this beta quantity, which we introduced and could be defined by ddt of log of the nucleation rate, take log of the nucleation rate and then take a time derivative. We can then switch this out for minus Hubble times the temperature times dd temperature of log of the nucleation rate. Just using this. And then log of the nucleation rate. This, if we have that gamma goes like some prefactor, I was going to call it A, but okay, I'm going to call it A again, times e to the minus this nucleation action that we had, evaluated on our bubble, or our bounce. Substituting that in, we get minus h times the temperature derivative of our action for the bounce. And what this tells us is that the bubble, or the bounce, gives us the time scale of the transition. So if you're interested in some particular model and you want to know how long does the transition take, you can work that out, because it's basically given by 1 over beta by taking a temperature derivative of your bounce action. Let's have a go putting in numbers to see, for an electric weak phase transition, what these kind of scales are. So we have this scale, which is an inverse time here. We have a scale here, which is the distance between bubbles, and then we have potentially our microscopic scales. So let's imagine we're interested in something which is of the electric weak scale. And let's ask, what's the average distance between bubbles? So this is roughly equal to beta. And beta is equal to, sorry, there was a mistake here. That should be a plus sign. Maybe you spotted that. Beta is equal to Hubble, and Hubble in radiation domination is T squared divided by m Planck times T. Or actually, let's do it this way around. This quantity here, which is dimensionless. And this quantity can be calculated in some model. And it has it's model-dependent quantity. It'll vary depending on the parameters of your model and so on. But a typical value for this dimensionless quantity is 100. So I'm just putting in a typical value for this bit here. Now if we put everything together, we're going to get 100 GeV squared times 100. So in the end, this is measured in GeV, divided by the Planck mass, which is 10 to the 19. So we get 4, 6 on the top, 19 on the bottom, so it's 10 to the minus 13 as our time scale. And writing this in meters to make it a length scale, and using the fact that a Fermi is roughly an inverse GeV, but there's a factor of 5, we get this is 1 over 2 millimeters. So that means for an electroweak phase transition, the average bubble size upon collision is 2 millimeters. So you can see them. For comparison, the Hubble the Hubble at the same time, which is just t squared over m Planck. This is 1 over 20 centimeters. So you have a 20 centimeter Hubble volume, and then your bubbles are roughly 2 millimeters across when they're hitting each other. For comparison, the temperature scale, which is 100 GeV, as a length scale is 10 to the minus 17 meters, or 10 to the minus 2 Fermi. So it's really microscopic. It's 100 times smaller than the width of a proton, right? So the microscopic scale is tiny, just as you'd expect it to be, but the bubbles actually collide really macroscopically. And that means, because everything is super macroscopic, because we have, whatever it was, 17 orders of magnitude, or many orders of magnitude between the microscopic length scales and the bubble length scales, no mass scales can be relevant for the description of the bubble growth. So the bubble growth has to be described by the universal effective theory on long distance scales, which is hydrodynamics. And the hydro is coupled to the order parameter of our phase transition, which is, in our case, this scalar field. So that means the dynamics of the bubbles, of bubble collisions and so on, let's say of large bubbles, it's governed by hydrodynamics, coupled to our scalar, or whatever order parameter we have. Because all kind of length scales that might be related to collisions and so on are going to be minuscule compared to these scales. So what does that look like? Hydro is determined by conservation of an energy momentum tensor. And we have the energy momentum tensor for a fluid. Which at leading order looks like this in gradients, and then you can write higher order gradient terms in an effective field theory expansion in long distances. But the next terms are the viscous terms. But at leading order, this is what your energy momentum tensor for the fluid will look like. And this is going to be coupled to the energy momentum tensor of phi, which is just what you would expect for a classical field, given that we're on such long length scales. All the quantum stuff should be disappeared. And the potential energy of the field phi enters in the fluid equation here because it enters the pressure and the energy density through the effective potential. So these two together will give us the hydro equations. We're going to need a separate equation for phi because this is not just determined by. So hydrodynamics gives you equations for u mu and the temperature as a function of position. Those 4 variables. This is 3 variables because it's time-like and a unit vector. So when we take the divergence of this, we get 4 equations. For those 4 variables, we need another equation for the scalar. And that equation looks like the following. It's going to be just the normal scalar dynamics, but coupled to the fluid. With dissipation, and I guess actually, whatever. So here, those 2 terms are the usual terms you might expect for the evolution of the scalar. There's additionally a term here, which is dissipation, basically. And it allows the scalar field to dissipate energy into the fluid. And then because we have dissipation, in principle, there's also fluctuation. But this is typically dropped. So these are kind of effective long wavelength equations. Oh, and of course, these 2 here will get d mu t mu nu total equals 0. That's the equation we'll get from them. And these are our coupled scalar and fluid equations of motion. This is a relatively simple, this is phenomenological equations, of course, but you can ask yourself the question, okay, can I derive these equations? If I started from my whatever model and I look at the very long wavelength dynamics, can I derive the form of this, and so on? Yeah, I guess that's kind of up for debate, let's say. So once you have these equations, they're just classical equations, you can numerically simulate them. And that has been how progress has been made in understanding what's going to go on in these bubbles. So one does numerical simulations, and the easiest thing one can do is just simulate one bubble and see what happens. So let's look at a single bubble. A nice property of the single bubble problem is there's only one scale in the bubble, in the problem. So in principle, there's the initial bubble scale, and then there's the later bubble radius. But at late times, the initial bubble radius is completely irrelevant. So at late times, there's only one scale, and that's the final bubble radius. And so you can divide out all dimensionful quantities by the final bubble radius and get a completely dimensionless scaling solution. So yeah, the whole problem becomes a scaling problem, a dimensionless problem. So there are scaling solutions at late times, which you can write in terms of the variable, the radius, divided by the time, or the time since nucleations of that bubble. So. And this is sometimes called zeta or something like that, which is your scaling variable that everything's going to depend on. And one finds 2 types of solutions depending on whether or not the speed of the bubble is faster or slower than the speed of sound in the fluid. So there are 2 solutions, or 2 types of solutions. Which one finds numerically? The first is the detonation. And if you plot the radial fluid velocity as a function of this zeta, then in the detonation case, you have a shock front, which behind it decays away. And the shock front is given by the location of the bubble wall. And because this is basically R over T, this is going to go up to roughly 1, between 0 and 1. So in some sense, we're plotting this quantity versus the radial bubble velocity. And so the bubble is moving fastest at the front, and then it's kind of moving a bit slower behind that. It's kind of, if you think about this, the bubble wall is moving very fast, so the bubble wall speed is greater than the sound speed. And the sound speed in a relativistic plasma is about 0.6 times the speed of light. So if our bubble is moving faster than about 0.6 times the speed of light, then we get a shock as this bubble goes through, because the fluid cannot propagate knowledge of this bubble in front of it because the bubble's moving so fast. So the only way that the fluid can know about this bubble is afterwards, after it's been hit, because perturbations in the fluid move at the sound speed. So basically you get the shock front and then a kind of wave behind that. And the other type of solution is the deflagration. And this is when the bubble wall speed is less than the sound speed. And in this case, plotted versus the same variable, again, the radial velocity of the fluid. This is the fluid flow outwards. This time, we have a slower, we have a shock here at the bubble wall. And one reason there's a shock at the bubble wall, the bubble wall is basically infinitesimally thin as far as the fluid is concerned. And this is because the bubble wall width is determined by like a microscopic scale, like 1 over the mass of the scalar. And the microscopic scales are infinitesimal compared to the fluid scales. So we get some infinitesimal kick, or infinitesimal in terms of width, kick to the fluid, and that's why we get a shock. But in this case, because the bubble wall is moving slower than the sound speed, in front of the bubble wall, you get propagations at the sound speed of the information of that, basically. So actually, let me draw this a bit higher up. So then we have it's not exactly flat, but something like this. And then this is a shock we get in front of it. And this shock moves with roughly the sound speed. In principle, you can solve these equations and not find a solution. And if you don't find a solution, it could be that there's no stationary value of the bubble wall speed in terms of these coordinates, which means that the bubble keeps accelerating. So that's a runaway solution. There is no stationary solution. And the dynamics of the rest of physics depends a lot on this. So for example, if you're interested in electroweak baryogenesis, which you'll learn about next week, it's much easier to do electroweak baryogenesis in the case where you have a deflagration, because you convert baryons, you create baryons essentially in front of the bubble wall here, and then they traverse through the bubble wall and then are kind of frozen out. And on this side of the bubble wall, you then don't remove any baryons, Whereas in this case, you don't create any baryons in front of the bubble wall, it's just in equilibrium. Then it gets hit, and after you're in the broken phase, then you don't produce baryons anymore. So which case really matters for things like electric baryogenesis also matters a lot for gravitational wave production. The gravitational wave production is quite different in these two cases. There I wrote that it all depended on this bubble wall speed. In terms of our phenomenological model, that bubble wall speed can kind of be switched out for this dissipation constant. So understanding which of these two cases happens and how fast the bubble moves, you need to do a calculation of basically dissipation of how the scalar gives energy to the fluid. But that will involve Boltzmann equations coupled to Langevin type equations like that. And is, I guess, an active field of research that doesn't feel at all settled at the moment. So we're not going to cover that today. What I'm going to go on to next is some more pretty pictures of numerical simulations. But this is the single bubble case. What happens if we just get a really big computer and put loads of bubbles in it and see what happens when they all collide? And I'll give you a kind of picture of the research that's been done in this field. So many bubbles. So I'll draw some boxes, and each box is going to be like a simulation volume at a time. So in the beginning of your simulation volume, we just have a bubble in it. This is nucleation. You evolve your nucleation a bit more, and then you get collisions of lots of bubbles. Okay, lots of bubbles. Something like this. And you're simulating this, and you find lots and lots of bubble collisions. However, what happens is, I mentioned before that hydrodynamics is the kind of unique long distance, long time effective field theory. That's coupled to this scalar at the beginning basically because of the initial conditions. But the scalar still will evolve on once the scalar starts hitting itself, it will still evolve on a quicker time scale than hydro. And this is essentially because, well, this is a massive field. It's not a massless field. So the mass will determine kind of how quickly it is relaxing, or okay, not just the mass, but the terms in the potential will determine how quickly this field relaxes. And it's going to relax much faster than sound waves in a fluid, which don't have a scale. It's a scaleless thing, right? They just keep moving. So after a while, right, your bubble collisions kind of calm down, and what you get is overlapping sound waves. I've tried to draw, they're kind of, the sound waves propagate out, kind of, they're produced when the bubbles collide with each other. It's extremely loud. But sound waves, to leading order, propagate linearly, and they just superpose. So they just keep going and they superpose. And the expectation is that at least depending a little bit on the situation, these sound waves can live for more than a Hubble time. So they're just hanging around, like superposing on top of each other. Then it's expected that after that, at some point, the sound waves start interacting non-linearly because hydro has non-linearities in it, and then you get turbulence. You get vorticity generated, and then you have the energy density moving to longer scales and to shorter scales. And then the turbulence, which is decaying turbulence, because we're no longer adding energy into the system. And then eventually, your box just looks simple and it has nothing in it. And you're just in the new phase. That's kind of the trajectory of what happens. It turns out you can't do all of this on one computer, so actually what has to be done is kind of people simulate parts of this and then match them together. But it's very much a kind of work in progress. This is, roughly speaking, the current picture. Some work has also shown that if you have deflagrations, which are in a strong transition, you kind of can skip out this sound wave regime and go to a different regime where essentially you heat up the region in front of the bubble so much that the potential starts changing shape. You start kind of heating up towards the critical temperature again. And at the critical temperature, there's no pressure difference making the bubbles expand anymore. So what you find is that these bubbles start growing, they heat up the fluid in front of them, and then they slow down because the fluid in front of them is hot, and that reduces the pressure for them to grow outwards, or provides a backwards pressure, in other words. And then eventually they really slow down a lot, and you get this kind of long-lived structures of this phase and that phase, which eventually probably goes here or there or something like that. So this is, what am I going to call this? Yeah. Plasma reheated, bubbles slow. What I've shown is the dynamics of what can happen in just this system, where we have a simple scalar order parameter coupled to a fluid. If your phase transition is a quantum field theory undergoing a different type of symmetry breaking, you can have, for example, if there's a Z2 symmetry breaking, you can get domain walls being produced. And if there's a U1 symmetry breaking, you can get cosmic strings being produced. And if there's an SU2 breaking to a U1, then you can get monopoles produced. And also there are scenarios where one can end up making dark matter in these little bits. So if you add extra ingredients on top of just this simple set of things, more complicated things can happen, and you can produce relics that can potentially live to today as a signal of the type of phase transition that happened. And I think you're going to hear a little bit more about this in some later lectures, but let's stop there for a 5-minute break.
With Oliver?
I had a couple of questions in the break about this. I just wanted to clarify that this thing on the y-axis is the velocity of the fluid going outwards in each case, whereas this bubble wall thing is the velocity of the scalar field that grows. Yeah. Just to clarify what the difference was there. So the next thing I'm going to talk about is something you'll have more chat about next week, and that's gravitational waves. And yeah, so I guess so we start from Einstein's equations, and what we're going to assume, we're not making black holes or anything like that, is we basically have a homogeneous background, and then we have some perturbations to that caused by all of this dynamics that we just described. So if we have a perturbation to the metric, the perturbation to the energy momentum tensor, where this will typically be RF, LRW kind of background. Then we can solve this equation. We linearize in the perturbations, and you can solve this, and then we just have a linearized differential operator. A differential operator acting on H equals some source. And you can just then write the answer in terms of a green function. So we're going to get this 8 pi on n Planck squared. Then we'll get an integral over our Green's function, which depends on x and y. And our Green's function, because the thing we're solving for has two indices, we'll have, this thing will have 4 indices and will contract with something like that. And then once we have our metric perturbation, which you can solve for from your energy momentum tensor perturbation, I guess you should put the y on the other side, but whatever. Then we can get the energy density in gravitational waves, which is equal to n Planck squared and 32 pi times the averaged energy in these metric perturbations. And this is the energy density in gravitational waves. And then if we've done our numerical simulations, we've worked out what T mu nu is, then we can do an integral and get what H is, and we can do some more integrals and get this. So you can get from your simulations with T mu nu, you can find out what the energy density in gravitational waves produced by your simulation is. And typically what people quote is omega GW, which is the energy density in gravitational waves divided by the total energy density from our background. And then we saw all of these dynamics, which I've just rubbed off, and what you find is that because gravitational waves are produced essentially linearly, and then they barely interact afterwards because their interactions are suppressed by Planck mass. The gravitational wave spectrum at the end is just the sum of the gravitational waves produced by each of the different processes. So our total omega GW is roughly equal to the gravitational waves produced by the scalar or the scalar bubble collisions at the beginning, plus those produced by the sound waves, plus those produced by the turbulence, plus anything else that's going on, like if we produced cosmic strings or domain walls or whatever else we produced, we would have a kind of sum of all of these sources. And then you can simulate these sources sort of separately and work out what the gravitational wave spectrum is for each one. So let's have a look at the scalar one first. In logarithmic frequency. So there's a scale which determines the peak, and that ends up being, well, let me just I'm going to denote by star means at time of the transition. This is somewhat standard thing, but so I multiply k by, to make a dimensionless combination, I multiply it by the bubble separation at the time of the maximum collisions. And I find something like this. my simulations. Actually, it doesn't look quite like that, sorry. It's more like this. So this is on a log-log plot. So this looks like so this is roughly pi in these units, where the peak is, and I have some power laws, so I have something like a k cubed power law in the infrared, and then I have a power law in the ultraviolet, which is like k to the minus b, where b is typically found to be between 1 and 2. So it decays a little bit slower. And then there's a second peak, subsidiary peak. Subsidiary peak at k is like the mass of the scalar. And on a simulation, probably you can only separate the mass of the scalar and the peak by at most 2 orders of magnitude, probably 1 order of magnitude. Whereas, as we discussed before, the size of the bubbles at collision versus the microscopic length scales will be like 15 orders of magnitude separated. So this subsidiary peak is really negligible in the cosmological case, even though in the simulations you see them next to each other. So this was the first thing to study because it's the easiest one to study. In principle, you can simulate this even without a fluid, just the scalar, and ask what happens, what does the scalar do in terms of the gravitational waves it produces, and you get something like this. But if you simulate, in addition, the sound waves, or the fluid, and you ask, what does the sound wave look like, or the gravitational wave spectrum of the sound waves, it's a bit more complicated. That's sort of roughly similar-ish. Measured in the same way, kr star. And you get a bunch of broken power laws. There's k cubed at the bottom, then it seems to grow like k to the 9, then like k to the 1, and k to the minus 3 in the end. And these power laws are definitely subject to some uncertainty, but essentially what's happened is some hints of these power laws at the top and right have been seen in numerical simulations, and then the numerical simulations have been modeled by something that can then reproduce these results, and then that model is extrapolated over here. And then people are at the point of trying to see whether the numerical simulations really do reveal this structure here on the left. But this is roughly what you see, and you get 2 peaks. And the reason you get 2 peaks is because there are 2 scales in the bubble growth. There's the 2 peaks. So there's one scale which is the average distance between bubbles, and that's our R star. But then there's another scale, which is the width of the shock front. So I had those kind of, in the deflagration case, or in both cases I had a kind of region where the fluid was moving, and this is basically VW minus CS times R star. And that gives the locations of these 2 breaks in the power laws. And for an let's say a typical electroweak-like case, one finds that omega sound is much bigger than omega GW sound is much bigger than omega GW scalar. Which is maybe not what you'd guess, that the sound waves are much more efficient or produce much more gravitational waves than the scalar field itself. This is essentially because the scalar field is short-lived in comparison to the sound waves, and we can see that by doing some having a little bit closer look and doing some order of magnitude estimates and some scalings. Let's actually have a look first at the frequency. This is an important quantity, it tells us where the peak is. We also want to know what the frequency is today to compare it to experiments. So far we haven't actually compared anything to an experiment, we've just done some simulations and looked at what comes out. So the frequency at the time of the transition, as I argued, is roughly 1 on R star. And this is roughly beta, which we calculated before, which is roughly, in a typical case, 100 times H star. Where this 100 number is absolutely model dependent. Which gives us 100 times T star squared on M Planck, assuming radiation domination. Now let's redshift to today. So we want F today. And this should be equal to F at the time of transition, appropriately redshifted. And the frequency will be decreased. So it's this way round. Where we have the ratio of the temperatures at the transition and then the redshifted temperature of the CMB today. And the scale factor goes like 1 over the temperature. So that means I can put in this ratio of scale factors I can replace by 1 over the temperature, the ratio of the temperature, so we get TCMB divided by T star times 100 times T star squared from here, divided by M Planck, or we have some dimensionless combination, and then we have cancelling one of the T stars. Dimensionless combination, this model-dependent number, and then the temperature of the transition. The model-dependent number depends on the nucleation rate and how that changes, and then this is just the temperature of the transition. And then this is obviously a small number. And if we again go for an electroweak scale transition, we can put in the numbers here, and we get that F today, the electroweak scale, is like 10 to the minus 2 hertz. And that is very fortuitously the experiment, or future experiment, LISA's optimum sensitivity. Which is great. It means that, in principle, if there's an electroweak phase transition and it produces enough gravitational waves, then it's going to be just in the right region to be seen by LISA. Also, if we were to consider, because the frequency scales positively with the temperature, proportionally to the temperature, that means if we look at higher frequency, so LISA's a low frequency detector compared to LIGO. LIGO's at like 4 orders of magnitude higher frequencies. That means LIGO and Einstein telescope and other detectors in that, ground-based detectors, are sensitive to temperatures 4 orders of magnitude higher. So if we look at for LIGO, Einstein telescope, Cosmic Explorer, which are all ground-based, their F sensitivity, which is like 10 to the 2 hertz, implies that they're sensitive to a transition of the order of 10 to the 6 GeV, or 1 PeV. Which means that these gravitational wave experiments at some point are going to be sensitive to energy scales which we can't reach in colliders. That's all well and good in terms of the frequency, but we also need to know the amplitude. Are we going to actually see them? Is the amplitude going to be high enough? So that's the next thing to look at. And for that, we would want to go back to our retarded Green's function that we had from before. And I'm just going to note that, so we had this retarded Green's function, and it had 4 indices. And essentially, you can split it up into a scalar part and a projection part. And the projection part essentially projects out what's called the shear stress, which is the transverse traceless bit of the energy momentum tensor. So we have, in terms of gravitational waves, what actually sources gravitational waves is shear stress, which is normally labeled pi ij, which is some projector acting on the energy momentum tensor. And then the scalar part of the gravitational wave Green's function in a radiation-dominated universe, so the scalar part of GR is then cos of k times T1 minus T2 divided by T1 T2. So that when we put it all together and look at the gravitational waves produced, it looks like an integral over T1, integral over T2 of this cosine, which is our Green's function. And then because we're interested in the gravitational wave amplitude, which is h squared, we'll get t squared over here. Or rather, we'll get the shear stress. So we'll get pi ij, kt1, pi ij, kt2, expectation value. So there's two t mu nus in there, or rather the shear part of them. And then there's the convolution with this Green's function, and that's what gives us sources gravitational waves. Now we can kind of estimate everything here. Everything is normalized by the total energy density. So these pi's are going to be, this is the energy density caused by the phase transition, and it's going to be normalized by the total energy density. So these pi's, this product of 2 pi's, is going to give us something like the latent heat divided by the energy, total energy in the universe squared. Squared because there's 2 of them. And then this convolution is going to give us something like t lifetime in units of h, and then t correlation in units of h. So how long the source lives for, and how long the source is correlated or autocorrelated for. Because when it goes out of, when it's no longer correlated, this cos is going to give us 0, basically. So it's only the bit where the source is correlated with itself that's going to contribute to the integral, and then because it's a double integral, it's also going to be the lifetime. So this is the general scaling behavior of the gravitational wave amplitude. And for a phase transition, we might expect that the lifetime, well, we've argued that the lifetime is roughly this 1 over beta quantity. So If we actually put in numbers, we find that there's some number out front times by this latent heat thing. And this number comes from simulations and it's absolutely rather a rough number. And then we're going to get this correlation and lifetime, which are both 1 over beta. So we're going to get h star over beta squared. That's for our correlation for our lifetime. It's just like very order of magnitude estimating. Now, if we think this is an electroweak-like phase transition where we have 1 degree of freedom contributing to the latent heat, essentially, and 100 degrees of freedom contributing to the bottom, then this is roughly 1 over 100. Okay, if you do a calculation, it can vary between many orders of magnitude. This can go above 1 and can below down to 0. But if we just roughly guesstimate it as everything has the same amount of energy, so there's 1 in the top and there's 100 in the bottom, then this would give us 10 to the minus 5 times 10 to the minus 2 squared. And then I gave this number before is roughly also 10 to the minus 2, because there's 10 to the 2 bubbles in each direction. So we get some 10 to the minus 13 out. This is just for like standard middle-of-the-road phase transition at the electroweak scale. And it turns out that the laser sensitivity is 10 to the minus 12 to 10 to the minus 13. So it's just a little bit not quite sensitive enough to be sensitive to a standard, like middle-of-the-road electroweak scale phase transition. But if we have a phase transition which is a bit boosted, it's a bit stronger than average, then the latent heat divided by the number of energy, this ratio won't be as small, or this ratio won't be as small, and then LISA will be sensitive to it. So LISA is only sensitive at the moment to slightly stronger than, or a bit stronger than average phase transitions. And the same, so if laser sensitivity, this number is also rather similar for Einstein telescope and Cosmic Explorer, but in different frequency ranges. But if you look at more kind of future projections of more speculative detectors, like DeSigo, Edge, Big Bang Explorer, stuff like this, their sensitivity is quoted in the range of, speculatively, 10 to the minus 14 to 10 to the minus 17, depending on which one we're looking at. So with these kind of future speculative detectors, we should be able to easily measure a kind of standard middle-of-the-road phase transition and even be able to measure potentially quite weak phase transitions. So this is kind of the expectation for the future. Yeah, and that's it. Thanks.
Is it a coincidence that laser sensitivity is so close to the expected amplitude and frequency in electroweak distancy? Was it one of the main goals of the?
It's one of the listed goals, and it was, I think, one of the reasons why. So LISA got downgraded to ELISA when NASA dropped out some years ago, and then the arm length decreased, which moved it kind of outside of the best window. But then when NASA came back in, the arm length grew again, and this was partly cosmologists saying, come on, we would really like it to be in this window. And I think it's also just as good for the people interested in astrophysics. So it's not like you lose astrophysics, but you do gain in this cosmological case.
Maybe the frequency of the vertical wave, what are we talking about? We don't have a coherent signal from batteries, right?
Yeah, so it's not a coherent signal, sorry. I didn't mention this at all, but it's a stochastic background. So you would see a superposition, a stochastic superposition of, so you're looking at the power spectrum of this thing, and you're looking at the frequency dependence of the power spectrum. So if you wanted to tell that this was a cosmological signal, you'd want to know that it's isotropic, it's the same in all directions, just like the CMB, and that it has the frequency shape that you expect from your cosmological model.